Hey guys, in this video we are going to be talking about exponential functions, specifically how to decide if a table represents a linear or exponential function and how to write the equation that goes with it. All right, so up at the top of page 14 in your notebooks, it says Introduction of Exponential Functions. So some functions model an initial amount that is repeatedly multiplied by the same positive number. In the rules for these functions, the independent variable is an exponent. So that means you have a number to the power of x. So we have yet to see that so far this year. So another definition here, an exponential function is a function in the form of y equals a times b to the x, where a is your starting value. So this here is your starting value. And b is your constant multiplier. And in the two graphs that you see, there are two examples of exponential functions. This one here is increasing, and I know it's hard to see in the graph there, but that's y equals 2 to the power of x. This one here is y equals negative 2 to the power of x. This one is an increasing, this one is decreasing. And then this one here is also decreasing. It's starting from the top and going down. That's y equals 1/2 to the x. And this one is weird, it's increasing. It's y equals negative 1/2 in parentheses to the x. So we kind of typically put the fractions in parentheses just so that when you go and start putting in values for x, they all come out correctly. So let's compare linear functions to exponential functions, because there are some things that are similar. They're just written in a different format. So you guys are pretty familiar with y equals mx plus b. We've used it all of first semester. M stood for your slope. That was what you changed by every single time. Now for a linear function, that slope is being added or subtracted constantly every single time. The difference for exponential is that you are multiplying rather than adding or subtracting. So m is your slope. B over here is your constant multiplier. You may also hear this called constant ratio. Both are the same thing. All right, now back to linear. We know that b stood for our y-intercept, which was always your starting value. Similarly, in the exponential form, we also have a start value, but it's not b, which can get confusing because both equations have a b in it, but the b in the exponential form is the constant multiplier rather than the starting value. The a, in fact, is the starting value. It's also kind of backwards from what you're used to. In slope-intercept form, the number that you're changing by is in the front and your start value is in the back. But in exponential, it's reversed. Your start value is in the front and what you're changing by is in the back. So try and keep that straight. All right, down at the bottom, it says with exponential form, notice that the input or independent variable is x, and a represents the starting value. B is the constant multiplier. So they have a couple of examples here, and you are supposed to write them each in exponential form. So first of all, we have 5 multiplied by itself 6 times here. That's the same as 5 to the 6th power, okay? Now, when you go to write an exponential equation that represents this, it's important to note that the multiplier rather, is 5, not the starting value. If you think back to when we talked about anything to the 0 power is 1, that's the same idea here. So there is no number here that we started with. We just started multiplying by 5s. So this is really a 1. So my starting value is 1. So when I go to write my equation, that would be y equals, There'd technically be a 1 here, and the 5 would go in parentheses, but since anything times 1 is itself, we write this as 5 to the x power, where you can start putting in different values for x, and you would just keep multiplying by more and more 5s. So let's take a look at one that doesn't have a starting value of 1, and that would be letter B here. If you notice, there's a 3 right here. This is my starting value. And then my constant multiplier is 2. Look at all those 2's. So here I have 3 times 2 to the, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 3 times 2 to the 9th. And if I wanted a general formula for what's going on here, it's going to be y equals 3, and then times 2 to the x. We typically write it like this, times 2 to the x. You could also write it as y equals 3, and then use the dot for times 2 to the x power. Both of these represent this over here. All right, so let's jump into determining whether or not a table represents a linear or exponential function. So if you're looking at these, remember that the main difference between linear and exponential is whether you are adding or subtracting or multiplying to change from one y value to the next. So you're trying to decide, all right, am I increasing by adding or subtracting the same thing every time, or am I increasing by multiplying by the same thing every single time? So the way that I do this is I kind of try and work backwards. So to go from 12 to 4, I could either subtract 9 or divide by 3, which means as I go down the table, I do the opposite. 4 times 3 is 12, or 4 plus 9 is 12. So those are my two options. So then you got to take a look at the second when you go from 12 to 36. Well, 12 plus 9 is not 36, but 12 times 3 is. So that means each time I go down the table, I'm multiplying by 3. Since I'm multiplying, that makes this table an exponential table. And then my equation would be y equals, my starting value is what y is when x is 0. So right here is my starting value. So that's going to be 4. And in parentheses, you're going to put your constant multiplier, which is 3, because I'm multiplying by 3 every time. And that's to the x. So the equation is y equals 4 times 3 to the x. All right, let's look at letter B. Here, to get from 4 to 7, I could add 3, or I could multiply by what is definitely a decimal. I don't know what that is off the top of my head. So I'm going to stick with the adding and see if that works down the table. So if I add 3 to get from 4 to 7, can I add 3 to 7 to get to 10? The answer is yes. So I am adding 3 down the table every single time. So since I am adding, that makes this linear. So I get y equals m, my slope, is what I'm changing by, which is 3, so 3x, plus my starting value is still whatever y is when x is 0, so it's plus 4. So that's the main difference. If I'm multiplying as I go down the table, I'm exponential. If I'm adding as I go down the table, I'm linear. And remember, it's the reverse order when you get to the equation. Starting value in front for exponential, starting value in back for linear. All right. Let's keep practicing here. How to write an exponential equation from a table. So I kind of went ahead and did that up here. All we needed to do there actually was to talk about whether it was linear or exponential. So everything that you're about to see here, I've kind of already talked about. So it has the steps for writing an exponential equation. First thing you got to do is find your constant multiplier, which is what we did above here. My constant multiplier here was 3. So then you need to also find your starting value, which is whatever y is when x is 0. So here, the starting value is 1. So I know it's going to be y equals 1, and then I'm going to figure out what my constant multiplier is. So they've already told us that these are exponential. So I know that I have to be multiplying by something. So this is my starting value. To get from 1 to 2, I would multiply by 2. And then 2 times 2 is still 4, so I'm multiplying again. 4 times 2 is still 8. 8 times 2 is still 16. So each time I'm multiplying by 2, so this is my constant multiplier. That's the number I'm always going to put in parentheses. So that means my equation is 1 times 2 to the x power. In this case, for this last one here, it'd be 1 times 2 to the 4th. 2 to the 4th is 16. All right, well, what about if we are decreasing in value rather than increasing? Let's take a look at how that works. Same idea, it's just that we're not really multiplying by a whole number anymore. So let's take a look. We don't know what the starting value is yet, but I know it is going to be here. Okay. Now, to go from 2 to 1, we know this is exponential, and I'm going to be multiplying by something. So you have to think in your head, what number can I multiply by to go from 2 to 1? Well, I know that 1 is half of 2, so maybe I'm multiplying by a half. Let's try that, okay? And then if I multiply 1 by a half, I get 0.5, so that makes sense. If I multiply 0.5 by a half, I get a fourth, which is 0.25, which means my constant multiplier is 1/2. So if I were doing this exponential form, this one here would be, well, I need to know what my starting value is first, I suppose. So let's figure that out. If I am multiplying by a half going down the table, I would be multiplying by the inverse going up the table. The inverse of 1/2 is 2, so I'm multiplying by 2, which makes sense. 0.25 times 2 is a half, times 2 is 1, times 2 is 2, times 2 is going to be 4. So my starting value is 4, meaning that each of my exponentials is going to start with a 4, have 1/2 in parentheses, and then you'll have x as your exponent. But for this table here, this first one would be 0. The second one would be 4 times a half to the first. Third is 4 times a half to the second, and so on. So that means my general equation is y equals 4 times 1/2 to the x power. So simple math here. Figure out what your constant multiplier is. You may have to find what the starting value is, and then write your equation. All right, down at the bottom of the next page, let's talk about the same idea, just with a real-world scenario here. So it says, evaluating an exponential function. Suppose 30 flower beetles, I don't know why there's an A there. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. Write the equation and find how many beetles there would be after 56 days, okay? So we know that the population is doubling, which means it's multiplying by 2 every single time. So 2 times 2 times 2 times 2, exactly, okay? And we know that it's starting with 30. So this is my starting value. This is my constant multiplier. So that means my equation is y equals 30, and in parentheses is 2, to the x power, where x represents the number of days. So I should write that. Let x rep number of days. From there, I need to figure out how many beetles there would be after 56 days. So I'm going to take my calculator here and figure that out. So I have 30 times 2 to the 56th power, because that's how many days have gone by, and I get a very big number. It's times 10 to the 18th, which I luckily have this out here. It is 7. Oh, hold on a minute. X represents, doubles each week. That's where I messed up. I knew that that was not right. So let's go back here a minute. So X doesn't represent number of days. It represents number of weeks. So we have to do a little math here before we keep going, because it doesn't make sense for my answer to be as big as it was. All right, so 56 days. We need to know how many weeks that is before we can carry on. So there are 7 days in a week. So I need to take 56 and divide it by 7. That is 8 weeks. So 56 days is 8 weeks. So I apologize for messing that up here. So instead of putting 56 in for x, I need to put 8 in for x. So it's y equals 30 times 2 to the 8th power. So let's type that into my calculator. 30 times 2 to the 8th power is 7,680 beetles. So 7,680 beetles. Again, don't make the mistake that I did. Make sure that you are using the correct units when solving these types of problems. Let's try another. An initial population of 20 rabbits triples each year. How many rabbits will there be after 3 years? All right, so I'm not going to make the same mistake again. I know that it triples every year, and they gave me 3 years, so I don't have to do any sort of calculation there. I'm just going to be able to plug 3 in. I know the starting value is 20 rabbits, so it's y equals 20. And in parentheses, I'm going to put a 3 because it's tripling each year to the x. So for this one, I'm going to take 3 and plug it in for x. Once again, I'm going to let x rep number of years. Okay, so I have 20 times 3 to the third, because it's 3 years, and that's 540 rabbits. All right, and that is a good introduction to exponential equations and how to write their equations given either a scenario or a table.